Okay, welcome everybody. It's what, June something? June 4th. Hey, we're getting there. This is our fourth class day. So again, this is my census day. So what I will do is look at the participant list and look at who's done homework and who was able to take the mock test. And all of those will contribute to your attending class and a positive mark on your census day. So make sure that you've done at least one or two homeworks. You just have to do a couple of them. You don't have to finish it, but that way I can see that happening. Okay, number two, I realize that we are slightly behind, so we might not get to our activity, which is the cyclohexane thing. If we don't get to it this week, I'll find some time to squeeze it in next week, because I really want you to have an activity to get those extra points for. But what I want to do is make sure we power through chapters 3 and 4 today, so that you will be prepared for your exam tomorrow. I have a couple people I'll be meeting right after this with trying to get Top Hat to work. I talked to Top Hat this morning. Most of you actually did really well, and you were able to log in and do everything like that. That's great. I have a couple possibilities for those of you who had difficulties, and we'll talk about that. You know who you are, just stay behind, and we'll start a new Zoom meeting for that at the end of the session. So I'm going to go through goals 1, 2, 3 of chapter 3 and goals 1, 2, 3 of chapter 4 today in preparation for what we're going to be doing tomorrow. Okay, our exam tomorrow. You should note that I've already started uploading number 5. All of number 5 should be uploaded by hopefully the end of today. There's a lot of videos for number 5, and because we're going to do a lot of different topics. And so go ahead and do that. Which platform will you post grades as they become available? Okay, that's a great question. I plan to post on Tracks for sure. I'm learning Canvas, so Canvas might lag a little bit. So I'm not counting on Top Hat Gradebook right now. I'm just using it as a way to get familiar with it. So count on grades once they're finalized after I what's the word, curve anything that needs to be curved. The grades on Tracks are the most accurate and probably most up to date. Okay? So, but I'm hoping to have everything transitioned to Canvas by the second half of the summer. So you'll see a lot of it moving more and more toward Canvas. Okay, excuse my cough. Okay, so let's see, any other administration stuff. So we're going to finish with chapter 4 today. We're going to have our chapter 1 through 4 exam on Friday. And then I will be posting chapter 5 and 6, 7, and 8 over the weekend, so you can start reading ahead as you have time. You can start watching videos ahead of time. Chapter 5 is kind of long because we're introducing the topic of mechanisms. We're introducing the topics of additions. And so it's broken out into, I believe, 8 videos to try to break it down into nice bite-sized pieces. I'm thinking about adding a 9th video, which is the compare and contrast. You know, these 3 things do this mechanism, these 3 things do that mechanism. So hopefully I'll add one of those, and it will also be on my goals slide as well. All right, is there any questions at this time? I am thinking about having a short Zoom meeting at 2 p.m. on Friday. I'm going to call it happy hour. What I'd like to have happen there is I'm going to open it up and say, okay, what's working, what's not, what can we improve on for next week to make sure that we're learning a lot, we're getting the information we need, we're getting it in the format we want. And so look for an invitation to our Zoom happy hour meeting. If of age, go ahead and bring an appropriate drink. If not, go ahead and bring a Diet Coke like I have right here. And we'll just talk and see what's working, what's not, and try to get our next week even better and more organized. Okay? Any other questions for right now? Okay, I have a Zoom, the group chat up here. And so go ahead and tap in as you need, and then I will start sharing my screen with my iPad here. Okay, so what I'm going to do here is I'm going to go with our chapter 3 goals. Okay, let me move this over here just temporarily. Okay, so again, the goals are things that we need to focus on as our primary thing that we have to understand to make all the other things understandable to us. So you want to think about the goals as, okay, if I have to start somewhere, I'm going to start with the goals, and then I'm going to add stuff to it, okay? So goal 1 of chapter 3 is understanding the idea that nomenclature and isomers of alkanes and cycloalkanes. Okay, so again, the general concept is that hydrocarbons are the basis of organic chemistry, right? It's carbon-hydrogen bonds, okay? Most of organic chemistry contains some kind of carbon-hydrogen bonds, and that's where we're going to start building our knowledge, okay? If we are saturated, that means all of the bonds, there are no double bonds, there are no triple bonds. They're all carbon-carbon single bonds. You can have other things on there, like chlorines and other things, but you cannot have double or triple bonds, okay? All sigma bonds, no pi bonds, okay? So, and that means the simplest of those is what we call an alkane. And that's completely saturated and it's completely open in a chain. It does not have any rings, okay? And that makes it our simplest. And so those are sometimes called aliphatic hydrocarbons. So you'll see that a lot in on the sides of containers. It'll say aliphatic hydrocarbon. And that just means it's completely saturated. It doesn't have any double bonds in it, okay? We will be tackling the other types, which are alkenes, alkynes, and arenes, but we're going to do those in later chapters. But right now, all we're talking about is carbon-carbon single bonds, okay? And because of the sp3 hybridization, they all have a tetrahedral geometry. So ideally, it's 109.5. Is it actually 109.5? No, it depends on how big the groups are next to it. So in methane, where all 3 of those hydrogens are equal in size and electronegativity, that will be 109.5. As you add larger, bulkier groups, that can twist things a little bit out of plane. But in general, they try to approach that 109.5 tetrahedral structure, okay? And it's all about the hybridization, the sp3 hybridization, okay? So when we draw these, organic chemists are kind of lazy. You don't want to draw out all the hydrogens, so we use what we call the line angle formula. I will also call it skeletal formula. And basically, it's showing you the important atoms, okay? So in the case of this stick drawing here, you have each line represents a carbon-carbon sigma bond, and the hydrogens are understood, okay? You just, if there's not a line there, you have to assume that the other bonds to make it that 4 bonds to carbon are hydrogens, okay? So, and when we go to alkenes, it's the same way. You want 4 bonds to carbons. The lines represent carbon-carbon bonds. Everything else is a hydrogen. So you need to start mentally adding those in, maybe start drawing them in as we start studying. And then as you go, you'll see, oh yeah, that's right, there's a hydrogen there. I don't have to worry about that. So here we have the end here is 1 carbon, and a sigma bond, 1 carbon, and a sigma bond, and a sigma bond here as well. So when we draw these skeletal structures, it makes it nice and easy to say, okay, that's where the carbons are. Anything other than carbon and hydrogen, I have to be very specific about. And we'll see that one as we add other functional groups to the system. Okay, so, and we need to memorize the first 4 names if you really are into the metric system and you understand the pentahexadeca. If you don't really like the metric system, then you're gonna have to memorize those as well. But 1 carbon is meth, 2 carbons is eth, 3 carbons is prop, and 4 carbons is butane, okay? And then everything else is a nice systematic forward above that, 4, 5, 6, 7, 8, 9, 10, all the way up to icosane, which is 20, okay? So all of these have this general formula of the CH2N, the CN, sorry, that's the number of carbons you have. So you're going to have 2 times the number of hydrogens plus 2 hydrogens. That's for all straight chain alkanes, okay? If you have a cyclic alkane, that means these last 2 hydrogens have to be clipped off to form the ring. So you'll see cycloalkanes will have CnH2n, or twice the number of hydrogens as carbons, because we have a carbon-carbon bond getting that terminus, that where that those last 2 hydrogens should have been. Note, it's the same general formula as if you had a single alkene. So if it's an unsaturated and doesn't have that +2 at the end, it's a cyclic alkane. If it's alkene, it can have that same formula. We'll see that when we look at the next chapter. Okay, so we have isomers available to us. And our naming structure gives us the idea that we can not be ambiguous when we name things. So we have a system that identifies different isomers, puts substituents in exact locations, so that if I say a chemical name and you write that chemical name, we're going to draw the same compound every single time because our names fit, okay? So our constitutional isomers change our name, change our properties, change our boiling point, change things. So that's why it's important to make sure we understand that we have isomers. As we move forward, isomers will also include things like cis-trans isomers when we have the cycloalkanes, and cis-trans isomers, EZ isomers, when we move on to alkenes. Okay. Let's move. There we go. So because of the adding, let's say we had a short chain and we just moved the methyl group from the end, we just keep moving it 1 carbon over, that chain, that gives you the potential for lots of different isomers. The more carbons you have, the more isomers you have. The more isomers you have, the more precise you have to be when you name them. That's why we have that IUPAC system. Okay, so I'm going to use the words suffix, prefix, and infix when I'm talking about these naming structures. The suffix is the thing at the end, the prefix is the thing at the beginning, and the infix is actually the thing that's going to tell us whether it's an alkane, an alkene, or an alkyne. Okay, so we're going to use those 3 words to tell us that the prefix is always the number of carbons. Meth, eth, prop, but. Okay, the suffix, which is the E at the end on this particular one, tells us the actual, that it's a saturated or has no double bonds in it. Or I'm sorry, the E at the end tells us that it's only a hydrocarbon, no other bonds but hydrogen and carbon. And the AN actually tells us that we have no double bonds, okay? And you'll see that that changes a little bit from this definition on this slide, because that EN means we have a double bond, that YN means we have a triple bond. But the E at the end means we only have hydrogens and carbons in the compound, okay? So that's the slight difference there. Don't forget, you can chime in and ask questions. It's, you know, we're a small enough group, we can do this, okay? Okay, so the parent name is always the longest possible chain, okay? And the reason we do that is because if it's the longest possible chain, that means it dominates the properties. So think about it as it's the biggest thing, it's going to be dominating the properties, meaning we need to name it first. Anything bonded to it is, of course, a substituent. And we name them alkyl substituents if they're hydrocarbon chains. Okay, in a general term, we can say the term R just means any alkyl chain that's hooked on to a main chain, okay? So we have certain groups that have common names, okay? And they have common names because they are they were, number one, originally named for this, and so they are used in a lot of different chemicals and in the chemical industry. So we tend to still use these names, even though we have a UPAC names for them. These make it easier to describe them. And so when we have a substituent that just has one carbon, we always say it's a methyl group. When we have a substituent with two carbons, that would be eth, but it's the ethyl substituent. So the YL just tells you it's that number of carbons as a substituent on a bigger chain, okay? So the next thing we get down to is propyl, and so that's the first isomer of 3 carbons we have. And then the second isomer of that is what we call isopropyl. Notice that instead of being a long chain, we've moved that methyl group over one. And so the carbon that's bonded to the main chain now has 2 different methyl groups on it. And that's the isopropyl group. We'll need to know this because we're going to use it a lot, okay? So then that we only have one isomer for methyl, 1 isomer for ethyl, 2 isomers for the propyl. When we get to the butyl, we have 4 isomers to deal with. So the first one's easy. We call it butyl or N-butyl because it's a straight chain, okay? The second one's called isobutyl because it's similar to isopropyl. So you take an isopropyl group and then add a CH2 to it to get isobutyl. So we'll see there that by adding this CH2 group here, we've added a carbon, so we get butyl part, but this still looks exactly like isopropyl. So it's isobutyl, okay? Now, instead of having this methyl group here, we move it over 1. So now that we have right here as a carbon, because we have this carbon has 2 things on it, we can call it sec-butyl, okay? Think of it that way, but it only happens in the butyl. Notice it doesn't happen over here in the isopropyl. It happens in the butyl, okay? So sometimes you might want to just memorize it as sec-butyl and not think about it as secondary. And then the last one is where you have all 3 methyl groups on the carbon that's bound to the main chain, and we call that tert-butyl or T-butyl, okay? These are all very common substituents. They're used a lot. Confused on the endings. Okay, I'm going to talk about the endings again right there because there's really 3 parts to each of these names, okay? There's the number of carbons part, there's the whether or not it's a saturated or unsaturated part, and then there other functional groups part. So there's really 3 parts here, and that's why I have those 3 names. We don't introduce the third part until later. And so that's what I will get to that question. I'm just going to continue with this. The YL at the end tells you that it's a substituent. If it's an alkane like butane, that means it's the main chain. Eel means it's a substituent. So methyl or butyl or propyl or pentyl means it's a substituent on a main chain. So whenever you see that YL, think of it as, oh, that's attached to something bigger than that group. The ANE that's the parent chain. The ENE, that's the parent chain. The YNE, that's the parent chain. Eels are always substituents. Okay, does that answer your question actually? Okay, great. Because we're gonna add to that when we do the infix part as well. Okay, so good. Getting that straight is important. Okay, so whenever we name our alkanes, if it's unbranched, we want the longest chain and it has an AN because it's unsaturated. The E actually means something, but right now, excuse me, we're going to start with the simplest saying. ANE means an unsaturated, a long chain, carbon, hydrogen, and it only has carbon and hydrogen, okay? That's really what the ANE means, okay? If you have branches, you name the longest chain you can and then start adding your substituents on there. Whenever you have a substituent, you take the number of carbons plus YL. That's telling you that that little substituent is hooked to a main chain, okay? So then if there's 1 substituent, we try to get it on the lowest number, okay? These are the first 4 rules of our alkane nomenclature. If there's only carbon and hydrogens, and no double bonds, we have the ANE, and the prefix is the number of carbons in that chain, okay? If you have a branch, you take the longest chain, name that with the prefix of the number of carbons in the longest chain, add ANE, and then you have to add the substituents, okay? And when you add a substituent, you take the carbon name, the prefix, meth, eth, prop, and add -yle to it to show it's attached to a bigger chain. When we number, we try to number so the substituent is on the lowest thing possible. And that brings us up to 3 and 4, okay? To add to that, we're gonna add another rule to that. If you have 2 or more of the same substituent, you can use di, tri, tetra, but you do not use it when we don't use the di, tri, tetra when we're doing our alphabetization. We're just denoting we have that many of the exact same substituent. So if we had 3 methyl groups, we'd call it trimethyl. If we had 4 ethyl groups, we would call it tetraethyl. Okay, so it doesn't matter how many we have as long as they're all the same. Now, when we name these, we also try to get to the lowest number possible first. So even if you have numbers that are like 2, 7 or 3, 9, you're going to want to start with the one that has the lowest number first. So the 2, 7 would be the proper one as opposed to a 3, 9, because you have the lowest number first. Okay, now this gets to our alphabetization here. If you have 2 or more different substituents, you name it based on the prefix, which is the number of carbons. So ethyl comes before propyl, propyl comes before, methyl comes before propyl, and then so you would have to think about those things as you put them on there. So as they grow in complexity, just put them in alphabetical order and then assign the correct number. Again, the number has to be on the lowest part first. If you have a choice of, oh, this will be a 3 on either one, you need to put the 3 on the lowest alphabetical number. So that's a subtlety, but you're still trying to use the lowest number and trying to use alphabetization at the same time. Okay, so if you have more than that, they do not count in alphabetization. But if it's a name of a substituent like isopropyl, it is counted in it. See, only multiples are not counted in alphabetization. Names of substituents are. That's a subtle rule, but it makes sense because isopropyl tells you what the whole substituent is. Di just tells me that I have multiples of a substituent. So the substituent, the alphabetization of the substituent itself, not how many you have. Okay, so that's the subtlety in our number 7 rule. Okay, so these are our first 7 rules, and we're going to build on these 7 rules as we go to alkenes and as we go to alcohols and all those things. We add additional rules to that, but these first 7 rules will always be followed. Okay, these first 7 rules will always be followed. All we're going to do is add to them with our next nomenclature section. Okay, sometimes we have to classify our carbons by how many other carbons are attached to it. And the reason we do this is, number 1, they have different reactivities. Number 2, when we create other things like charged species, certain species are more stable than others. By identifying how many other carbons are attached to a carbon, it helps us rack and stack where the reactions are going to happen. So the simple thing to think about is if my carbon has 4 other carbons, that's quaternary. If my carbon has 3 other carbons and a hydrogen or something else, then it's tertiary. If it has 2 other carbons, then it's secondary. If it's at the end of a chain, it's a primary. Okay, so think about end of the chain is primary, the middle of the chain is secondary, a middle of a chain and a branch point can be tertiary or quaternary if it has 2 branches on it. Okay. okay? So that rule takes us up to all of the straight chains. Now, once we take a straight chain, and if we take a hydrogen off the end and a hydrogen off the end and put those together and form a new carbon-carbon sigma bond, we now have a cycloalkane. So the only thing that's changed is we've lost 2 hydrogens, but we still don't have any double bonds. We still have no other functionality, okay? That's why the general formula changes, is we've taken those 2 hydrogens off the end and created a new carbon-carbon bond, okay? These are most common in 5- and 6-membered rings, but as I said before, we can go from a 3-membered ring to a 100-member ring. And it'll go anywhere in between, but the most commons are 5s and 6s, which is why we have special names for them, and we look at the flipping of different isomers back and forth, okay? So this is typically done by taking the prefix name, which remember is the number of carbons that would be used to make that ring, and add cyclo to the front of it. So if it's 5 carbons in a ring, it'd be cyclopentane. 10 carbons in a ring, cyclodecane. Okay. If there's only one substituent, you know that has to be the number 1 position, because it's the only differentiation in the ring. Where do you start a ring? You know, the ring is continuous, it goes around and around, right? So you don't have to number it unless it has something on it. And if it has something on it, that's where you start with number 1. And if you have more than one thing on there, try to get the lowest number possible. Okay. So that gave us to these different little things. Notice we have the isopropyl is our substituent on the cyclopentane, okay? Whenever we think about naming things, okay, and we have a ring and a straight chain, whichever has the highest number of carbons becomes the parent. So you can have a long chain with 9 carbons on it and have a cyclohexane hanging off it. You're going to name it for those 9 carbons first, and you're going to put that cyclohexane as a substituent. So if we have a substituent, we have to drop the end and add YL. So it'd be cyclohexyl, or 1-cyclohexyl nonane, for having 9 carbons in our hydrocarbon. So the longest chain, even if it's in a ring, counts as the primary name, and then we add our substituents from there, okay? And I went through all of these in the video, but the idea is that even if you have a ring and a straight chain, the highest number of carbons wins as parent, even if it's ring or a straight chain, okay? So this is where I got into the thing where there's a thing called an infix. When we first started the chapter, it didn't tell us about the infix, but the infix is important when we move to double bonds, triple bonds, okay? So the prefix is always the number of carbons. Meth, hep, pro, but, tert. I'm sorry, not tert. Penta. Okay, so the prefix is always number of carbons. The infix tells us whether we have single bonds, double bonds, or triple bonds, okay? So that's an AN for single bonds only. An E is 1 or more double bonds, and an IN is 1 or more triple bonds, okay? Notice 2 double bonds does not make a triple bond. If you have 2 separate double bonds, that is not the same as a triple bond. So that's why they are completely different. And then the last thing, the suffix, the E at the end or the YL at the end, tells you about the class of compound, okay? So in the case of a hydrocarbon, if it's not a substituent, we put an E, saying that there's no other bonds, just carbons and hydrogens and no other bonds. If it's a substituent, we add YL. The YL tells us it's a substituent on a main chain, which means the suffix on the parent chain, if it's only a hydrocarbon, will have an E at the end. Okay. Now, as we add functional groups in later chapters, we're going to see that end part, that suffix changes. So when we create an alcohol, we'll have an OL, an aldehyde, an AL, a ketone, an ONE, and then when we get to the carboxylic acids. And what we'll find is, as we go up, they have a priority, and carboxylic acid is the most complex of the of the functional groups. So it will actually, if you have a carboxylic acid anywhere on the system, it'll end up naming your system. But that's just to give you an idea that that's where we're going. We're going to add these one by one, and so you will see the priority as we add them one by one. So prefix is number of carbon. Infix tells you double bond, single bond, triple bonds. Suffix tells you what the compound's named for, or what its functional group is. Okay, so that's goal one, all right, is that we have it broken down into a system of rules. We follow the rules in order, and we're going to add to those rules as we go. All right, any questions on chapter 3, goal 1? Okay, while you're putting those in the chat, I'm going to pull up chapter 3, goal 2. Right here. Okay. So this is a little bit shorter, and it's because when I first started doing this, we did a little bit of physical properties and a little bit of not, a little bit of physical properties and not, and so what I want to do is draw almost in each of our functional groups. I want to draw out the physical properties and the types of bonding it does. Okay, because as we change functional groups, the type of interactions that those compounds have changes. So I want to make sure we draw that out specifically as a goal, and it doesn't get buried, okay? Because alkanes, that carbon-carbon bond is nonpolar, and the carbon-hydrogen bond is really nonpolar too, there's not very much reason for the molecules to interact, okay? And because this is a weak interaction, we call this, really, it's an induced dipole, meaning they don't really have charge, but when you put two things close together, one side will say, oh, I'll move my electrons to one side, and then this side becomes more partially positive. And so then this side will be, oh, I can be partially negative, and I can pull electrons away from this side. And so we're temporarily creating this little teeny dipole, and then of course, it'll kind of bounce back and forth, back and forth, back and forth. So it's a very weak force, and it's the only force these things have. As these molecules kind of lie across each other, the more that they can make these induced dipoles, okay, there's a little more interaction here, but it's still a very weak interaction. So if we had a long chains, they tend to have more of the surface area is interacting than if we had short chains. So that's why the forces get bigger as the chains get bigger, okay? That's why the forces also change as the molecule changes shape, okay? So when we have it out as our extended full length, straight hydrocarbon, we want to have it extended out in what we call that zigzag pattern, because that has everybody in their tetrahedral geometry. Does that mean that all hydrocarbons are straight chained like that all the time? No, we have free rotation around each of those bonds. There's going to be some motion going around there. But the average of all of those motions is going to give us that this straight chain is probably there the most of the time, and then we'll have other, where it's kind of folded up a little bit like a ball sometimes, but it's going to open up. And there's not really much of a barrier for it to do that. So when it's fully extended, it can have the greatest interaction with other molecules, giving us that van der Waals forces. And that's why, the longer chains start to have higher boiling points and start to have higher melting points, because there's more and more of that induced dipole or dispersion forces. Okay. That being said, if we have just the one or two chains, we have very small amount of interactions. The boiling point is driven by two things: the molecular weight of the compound and its interactions, okay? So if we take every compound, it just says, oh, it has a molecular weight, so part of its boiling point and melting point is going to be defined by its molecular weight. The rest of the boiling point, melting point is defined by the types of interactions it has with other molecules. So in these hydrocarbons, we have those very weak little interactions. So the dominant force in hydrocarbons is their molecular weight. The secondary force is that weak van der Waals or dispersion forces. Okay, that weak dispersion forces. So that means as we get more and more carbons, we have higher and higher molecular weights. Okay, so that's very important to know. And these are carbon-hydrogen bonds are not very polar. So, and they're trying to spread out in this tetrahedral structure, so that lowers their density a little bit. Almost all of the hydrocarbons float on water. Almost all of them are less dense than water. Even when we get to really high molecular weights, these tend to float on water. Okay. So I said that the amount of interaction between them is one of the forces, and the molecular weight is the other force. Okay. We can demonstrate that amount of area, surface area, controlling that by looking at isomers that are more spherical. For example, in this bottom one here, we have, oops, no, not that. There we go. In this bottom one here, we have two of the methyl groups have been moved from the ends of the chains to the middle of the chain, and it's starting to look a little more spherical, okay? And we'll see that because in the long chain, we have an overlap of up to 6 carbons, giving us that dispersion force for up to 6 carbons between this one and that one. And so that's going to drive the boiling point and melting point up because of the addition of the dispersion forces to the molecular weight. My watch is trying to make me exercise. It will be disappointed. Okay, so as we change the amount of interaction, the number of atoms that can react with each other, and we make them more spherical, there's only a few interactions between this spherical molecule and this spherical molecule. Therefore, it's dominated by the molecular weight is controlling its physical property, not its dispersion forces, because it has very few dispersion forces. So that kind of thing, I think, is really important to think about, because dispersion forces are only thing in hydrocarbons. As we move on to functional groups, we're going to start to add other things like dipole interactions and hydrogen bonding, okay? But what we want to start with is the idea that dispersion forces and surface area and molecular weight are the first 3 things we're going to use to determine the physical properties of these materials. Okay, so, and then of course we get most of these from the ground, either through petroleum, natural gas, or coal. And I found a really cool distillation in motion kind of thing, but it wouldn't translate to the PDF. So maybe I'll give you the link and you can go see it yourself. Okay, any questions on goal 2, physical properties, okay? We are missing this part of the slideshow, an individual slide. Let's see.
No, it was like the last topic that you covered. I don't see anything about that in here.
It's definitely in Top Hat. Let me look in.
A little bit further on. It skips a lot of other stuff, but it's further on in the PowerPoints.
Yeah, the goals slides are in a separate place. There should be slides goals and slides videos. So
okay,
in slides goals, there's you know, there's a couple slides I skip over because I'm talking through them as I go, but I think they seem to be all on my Canvas site. Take a look. Okay. All right. So that was just to give us an idea about properties, because it's going to become more and more important as we go to other functional groups, but I thought it was really important to keep us thinking about properties and where they come from to start with, okay? The last thing that I want to talk about as a goal for alkanes and cycloalkanes is the idea that there are very few reactions that these things do. And it all comes down to the idea that we have an sp3 hybridized carbon bonded to an sp3 hybridized carbon. That's a nonpolar bond. And then we have a bond to hydrogen, which is also a very nonpolar bond. polarity of bonds is we're gonna see reactions are related to polarity of bonds and where the electrons are, okay? In this case, because of this type of bonding, this sigma bonding, and it's a nonpolar bond, we have very few things it can do, okay? So of these classes of hydrocarbons, we'll notice that we have no double bonds, we have no polar bonds that can do other chemistry. So that makes them do only a couple things, and one thing is burn. Once we get to having this pi bond here, we'll see that gives us reactivity. That gives us electrons outside of the plane of where the atoms are. And those electrons outside of that plane gives us reactivity and things we can do, okay? And then when we go to alkynes, we have two of those pi bonds we can play with. And when we go to these, the idea that these are alternating back and forth, single, double, gives us a whole other chemistry associated with it. And we'll get to that in the next chapter. But so that means oxidation is one of the few things we have that alkanes do, okay? We can burn them, basically, okay? Now, one of the interesting things that the burning can tell us is that by the amount of heat released, it tells you the amount of energy that was stored in that material. And we call that energy density. Or, you know, hey, if I burn methane, it's going to give me so many kilojoules per mole. And in this case, it's 886 kilojoules per mole. And that's heat released. The negative means the heat is being released into the atmosphere. It's giving it away. It stored that energy, and now it's giving it away. So it's only 886 kilojoules per mole, okay? Just by adding two more carbons, going from methane, which is natural gas, to propane, which is in your propane cylinder on your barbecue grills, we actually get not quite 3 times, almost 3 times more heat out of the system. Almost 3 times more heat is stored in that compound than was stored in methane, okay? So once we completely oxidize it, it completely oxidized down to CO2 and water. So its only byproducts are 2 gases, CO2, greenhouse gas, that we can harvest and use for other things, and water, which we like to use on a daily basis, okay? So the heat of combustion is really telling us about how much energy is stored in our hydrocarbons. Okay, so I kind of looked at this and went, do we really want to think about this? And I think the answer is yes. Coal is actually tends to be not a hydrocarbon itself, but tends to be a carbon, specifically a whole bunch of carbons bonded to a whole bunch of other carbons, typically 3 carbons, so it's going to be sp2 hybridized in this huge big field, okay? This is different than diamond. Diamond is your carbon that is sp3 hybridized and is bonded to 4 other carbons in a nice tetrahedral structure, okay? So that's diamond, okay? And that has different properties than coal. Coal is sp2 hybridized and makes sheets, okay? And so that we have to take that carbon and add hydrogen to it by superheating with water to first generate CO2. And then once we, carbon monoxide, once we generate carbon monoxide, we can then turn that into viable products like methanol and acetic acid. In fact, down on the Texas coast, there's huge towers out there where they heat CO and hydrogen and methanol and CO to create methanol and acetic acid. I went and toured a couple plants. They're really kind of cool. It's massive plumbing on a weird scale. But so these hydrocarbons really don't do much other than react with things at high temperatures and usually in an oxidative process, okay? Yeah, and right now we are in a petroleum economy and we'll have to move away from it because we only have so much coal and petroleum actually underground. There is a limit to how much was stored there in previous geological cycles. And so coming up with new chemistry to create new hydrocarbons from surface synthesis is actually a really big driving force. There's lots of opportunity for new chemistry and new environmental developments related to that. Okay, so that is our goal 3. There's very little reactions we have with hydrocarbons, but we're going to see that change as we move to all the other functional groups we have. Okay, questions on that? Okay, I'm getting ready to go ahead and take our first break here. And what I'd like to do is I would like to get all caught up and do our goals for chapter 4 first. And if we do have time set aside, I have this exercise with cyclohexane flipping that we'll start. And if we don't have time for it today, don't worry, we'll catch up with those points next week, okay? So any questions on chapter 3 before we take our first break, and we'll come back in about 14 minutes at 1 o'clock. All right, I'm going to stop recording.